Welcome to my live stream. All right, you see I've already started doing a little bit of work on this mission. What I'm basically going to do is start coding the flyby to Minmus mission. Now, I'll be doing this the traditional way from a parking orbit around Kerbal. I won't be trying to fudge this one. Now, Minmus presents a couple of challenges, so we'll deal with them one at a time. And yeah, it's going to get a little bit mathematical, unfortunately. But I can't really help that. Now, you can see that's the orbit of the Mun there, and you know that's got an inclination of 0. It goes directly above the equator. Now you can clearly see the orbit of Minmus is this is a trick to have a look at the angle. Not that it lets you get it. Yeah, so that's the equatorial plane there, right there, and you can see clearly that Jesus, it doesn't let you do. This game just does not let you do precise movements. Not with a mouse. Anyway, you can see that the Minmus is inclined. It's about 5 or 6 degrees, I can't quite remember. Now, to make your life simple, you start off from an equatorial orbit, and then you've got to do a plane change maneuver to align with the plane of Minmus. So that's the code we have to write first to do a plane change. Now, it's going to be interesting. It's going to be some maths. I can't avoid it. I do already have a routine ready in case it's one I've used before in case I get stuck. But I'm going to try to write a new one right in front of your very eyes that will automatically do a 5 or 6 degree plane change to line up with Minmus. There's some other complications as well, but let's just go through them one at a time. So that's the first thing that we have to do is this plane change. Now, plane changes only make sense if you can see it's not just come out with an inclination of 5 or 6 degrees. You've got to also do it in the right spot. Otherwise, you might just have the plane might head off in that direction or whatever, and it won't do you any good. So you've got to line it with Minmus as well. So that adds another complication to things. Now, you've probably already heard of this before. There's these things called the ascending and descending nodes. So it's about 6.6 degrees, right? So okay. So you may have already known that you can only do your plane change at these points, either at the ascending node or the descending node. Now that begs the question: how do you work out where the ascending and descending nodes are from a kOS program? Now, when you wanted to God, that's pretty. Oh, okay, yeah, all right. That's just by convention. Yeah, I'm struggling with that orbit. Actually, there's something wrong with my launch to orbit routine, but I'm just going to have to look at it carefully. It's firing a couple seconds late. That's why I can't get a good orbit. Anyway, let's just ignore that for now. Now, you already know that a kOS script will tell you how many seconds you've got to go before you hit the apoapsis or periapsis. Your vessel will hit the apoapsis or periapsis. It's called the ETA variable for estimated time of arrival, and that's all great. That the game calculates it for you. Now the trouble is it does not calculate a similar thing for ascending or descending nodes. It it does, but it's way down in the guts. Obviously, it's displaying it, so it knows it's there. It's way down in the guts of the program, and it's just not available to kOS scripts. So we're gonna have to calculate that ourselves, and that's interesting. That's very interesting. All right, so we just have to start at the beginning. I'll just have to go through one step at a time. It will be, now will it be a library function? Not really, it's a maneuver. It's a maneuver, so I wouldn't normally put that in a library because there's always going to be something fiddly you have to allow for. So let's just call it, I'll try to make a generic one because it can be useful for other reasons as well, other purposes as well. Okay, so I'll start writing it. I'll write it as a maneuver now. I think that's probably the right thing to do, but we will parameterize it. So local function. It's not somewhere. And we'll just call it plane change. Do plane change. Do plane change. Plane change. And it's, you know, you can assume that you're talking about the vessel, so you don't have to do plane change on vessel or something. That's a bit of overkill. Right. So just say do a plane change maneuver. All right. Now there's kind of two types. I'll stick with the first type for now. Now that's because you're doing it. If you were just going to do a plane change, you could do it. You could do it anywhere. You wouldn't have to worry about where you did it. But that's not what we're doing here. We're trying to do a plane change for a planet. That means I'm going to have to rewrite this slightly. How best to word it? Just say do target, do plane change. I'll just call it. Might think of a better way of naming it. Do a plane change maneuver relative to a target. Now you would assume that you know that the target's either going to be a vessel or a. I'm not saying what it's going to be. It could be a vessel, it could be a body. So that's another reason why I want to parameterize it, because if you write one that works for movements, you can also write one that works for another rocket. When you're doing intercepts and stuff like that, it can come in handy. So we want to parameterize it. We'll just call this one actually I'll spell it out. Target orbit. It's called an orbital. An orbital. Now, an orbital can be either a body or it can be another rocket. That's an orbital as well, or it could be an asteroid. Stuff like that. So anything that's kind of in an orbit, we can target with this maneuver. All right. So let's just call this. I don't know if orbital might be a reserved word. I don't know. We'll pass it as a parameter anyway. We'll just call it orbital. So it's going to be passed in which orbital that you're referring to. All right. So, gosh, where do we start? Where do we start? Where do we start? All right. Well, we already know where the orbital is. That's okay. So we've got to work out the ascending and descending node for the orbital, which is this line here. from there to there, even though they don't show it. They sort of show the outside line, but they don't show the inside line. Like so, it's actually called, they call it the line of nodes because there's two nodes and they line up. So it's called the line of nodes. That's a technical one technical term for it. So we're going to have to work out where the where the line of nodes is first. Now that's not too hard actually. You do something really strange, really strange. Gotta remember the equation off the top of my head. If I get stuck, I'll look it up. I might need to refer back to the manual a couple of times, but bring it up. Yeah, so I'll come up with some jargon, but I won't explain exactly. I won't give you a full depth analysis of it unless somebody asks me to. If somebody asks me to, I'll take the time to explain it as I understand it, but I'll just kind of state it as a given. Now, here's the thing: is if you've got this, you can see planets and also spaceships. They basically, an orbit is a plane. There it is, right there. You can see it. You can call that a plane, right? And that's exactly what they mean by plane change. Now, so it defines a plane. Now because things are going around in the plane, they in effect have a type of momentum associated with them. Anything that's rotating in some way has got momentum, rotational momentum. And if it's got rotational momentum, it also means it's got an axis. Because like an imaginary line that everything is spinning around on, and the axis points up and down. So it's just like a gyroscope is one way of thinking about it. So it defines an axis. So this line here actually defines the plane because it's a flat line that lies on the plane. So therefore that defines the plane as well. So that the line of nodes actually defines the plane. But the thing is, it's also got an imaginary axis, one that points up and one that points down. And you can think of the whole axis as being spinning in a certain way, but it's a type. It's what they call the technical term for it is. This all will become relevant, by the way. I just got to get the jargon right. Where's Wikipedia? It's called the specific orbital. It's called, we call it SAM for specific angular momentum, but I think they've got a slightly different term for it. They call it a specific orbital energy. Right. Okay. And it's a type of angular momentum. Actually, it's called the specific relative angular momentum. I just used to think of it. I called it SAM. It was a lot easier to remember. So we're going to have to work with this SAM thing. And believe me, there's a lot of horrible equations here, but I think we can do it in an easy way. So what you do is you work out the SAM. You work out the SAM for a body or whatever. It's called the orbital. And now let's just call it local. Let's just call it SAM for now. How can I specify this exactly? Right. Okay. Let's just call it SAM. 1, 2, and it is what they use this vector thing called a cross product, which is abbreviated. Let's use the abbreviations, it gets too long-winded. Called a cross product. It's called a vector cross product, and the abbreviation for it is VCRS. So it's a VCRS. Now it's got two parameters, and they're both vectors. Now the first parameter, I think it's commutative. I don't think it matters which one you put. I don't think order is important. Hang on, just better check it's not important. I don't think it's important. Yeah. I can't quite remember if it is important or not. It could be. Either way, whatever you do, be consistent about it. What does Wikipedia say? Drew me up these equations. Let's see the equation. We're using the yeah. Don't actually see it. I can't remember the You're not helping me out here, Wikipedia. I'm going to get this wrong. Alright, hang on. I'll find it. Specific, I know what it is. I just got to get the terminology right. I wasn't going to lead people astray. Hang on. It's the there's God's blood. Stupid looking Google AI just takes everything from Wikipedia. Oh, that's wonderful. It's exactly the same definition. The formula. Gosh, hang on. I'll say specific orbital energy cross product. Okay. I don't know if it's, I guess we're going to find out if it's all right. Well, that's how you calculate it. So it's the going to be the orbital position vector, cross product of the orbital position vector and the orbital. Better make this orbit orbit. Trouble is going to be orbit, velocity orbit. It's going to look a bit strange. I think that's about right. So basically, it's a cross product of the position vector and the velocity vector. Pretty much. So there's two ways of looking at the world when it comes to orbital mechanics. One is you can use the orbital elements, and there's about 5 of them. Those are the ones that were worked out by Kepler, and he's and the people that came after him a long time ago. The other way to look at it is from the vectors, and there's only 2 of them basically that define just about everything. One's a position vector and one's an orbital velocity vector. It just makes everything a lot simpler, in my mind anyway, because I'm good at working with vectors, but I'm terrible at working with trig. So I like to think of everything in terms of vectors. I can explain what these things are. By definition, the position vector is basically a vector that points from the center of the body you're orbiting around to the center of your orbital. So it defines at all times you think about it, that direction and that length defines where that body is in its orbit at all times. So that's easy. And the velocity vector is always perpendicular to that. It's actually I won't call it the speed, it's the velocity of the object at all times, and it's another vector that's perpendicular to the position vector. And then say it points out in that direction from there to there. It'll tell you how fast the speed of the object and the direction that it's traveling in relative to the center of this body here. You always need a reference point for any of this to make any sense. So it's one way of looking at it is you can use the five Keplerian elements to define the position of an orbital, or you can use two velocity vectors. So it's your choice, whichever you feel comfortable with. I'm just trying to remember the exact term for all this stuff. They call it the hang on. I just want to get the terminology straight before I move on. See, I'll call it orbital elements. And the game uses both of them. It uses both systems, and it swaps between them. The orbital state vectors, that's what I was looking for. The orbital state vectors, and there's pretty much only 2 that you really need to worry about. So one is a position vector, one's a velocity vector. Oh, there's also an epoch, but we'll talk about epoch at some other time. So I like to think of it in terms of position vectors. The orbital state vectors, that's a bit more physicky in my mind. But the Keplerian ones, we've got eccentricity, semi-major axis, semi-minor axis, the semi-parameter, the apoapsis, and the periapsis, and you've also got an epoch as well to define when the whole system started up. So yeah, take your pick, whatever you feel comfortable with. You can use either one. They'll give the same result in the end of the day. So all right, we've got that, and so that's how we define the SAM. Now, well, that's all well and good. It's all we've done is defined an axis that points up that way. It's actually perpendicular to the position vector and the velocity vector. So the only position left to you is that one there. Okay, so now if you do something really weird, you take the cross product again. I can't quite remember how to do this now. I might have to look it up if I can't remember it. This is why I write scripts, so I don't remember this stuff. It's the line of nodes. From orbital state vectors. The line of nodes can be calculated by finding the cross product of a vector normal to the reference plane and a vector normal to the orbital plane. Gotcha. You got to work out two SAMs. That's it. That's the trick. You work out one SAM for your orbital. So that'll be orbital position, orbital orbit, velocity, orbit. And the second SAM, which we'll just call SAM2 for now, can't think of a better name, is a reference frame. And I just happen to know for a fact that the equator is used as a reference frame. That basically the plane that cuts through the equator is the other reference frame of the thing that the orbital is orbiting around. So that's the second one. So you work out its specific angular momentum exactly the same way. So you just say ship body, because you're still orbiting around Kerbal, right, at this point in time. Ship body, ship body, no, sorry, am I getting this right? It's got to be ship body, the ship body position. Seems a bit odd, doesn't it? Because it's not actually moving. Oh no, sorry. Take it one step back. Sorry, I said something wrong there. I said something wrong. I didn't mean. Sure, yeah. Kerbal's got a reference plane, which is the equator. I'm talking about the orbit of the ship. Has also got a specified angular momentum, and it may or may not be going. It's going around the equator now, but it may not be. Could be at some other angle. So we actually need the one of the ship. So ship. It's got to be. I've got to offset it. Ship position minus ship body position. But just trust me on this. And ship orbit, ship orbit, orbit velocity, orbit. God, what a mouthful. I've seen worse. So we've got that one. So the local, that means the line of nodes, which I'll just call line of nodes. Now these even though these are stored as a vector, they look like a vector, they smell like a vector, and they sound like a vector. They're not vectors. They're actually what they call a pseudo vector. Oh boy. Mechanics know what a pseudo vector is, especially car mechanics. Well, guys who design cars do, especially car tires. That's the analogy you use. So anyway, it comes back like it looks like a vector, but it's not really a vector. It's a pseudo vector. And I'm going to look it up, the definition. I can never get it right in my head. but mathematically, you treat them as the same. That's why they're called a pseudo vector, even though it isn't a vector or something. All right, okay. Anyway, I like to put vec on the end of my vectors just so I know what I'm dealing with. So the line of nodes is just simply the VCRS SAM1 vec. And if I get everything around the wrong way, I guess I'll find out when it doesn't work. SAM2 vec. Okay, so now we've defined the line of nodes. Okay. Why is it complaining? Oh, right, sorry. 2, 2. So that's the equations. That's it. That's the mathematics. So it defines the this thing called a line of nodes. Great. We've got a line. Doesn't really help us much. It's just kind of sitting there. But it's, you know, it's an intermediate result that you need to actually, sorry, let me see what my voice is sounding like. It's just kind of sitting there. Right, okay. Now, so just getting back to here. Okay, we've just now defined a vector that goes out that one, which is basically that dotted line. In effect, that's a vector. That's it. So it's just telling you, all it's telling you is where the plane of minimus crosses the plane of your spacecraft. Pretty much that's all it's doing. All that mucking around just for that, but that's the way it is. That's all it's telling you. It's telling you where your where these 2 points are. Now, great. Well, what you really want to know is how long it's going to take your orbit to hit those points, because you've got to time your burn. If you're going to do a burn at those points, you want to know how long it's going to take your ship to orbit that particular point. That's the that's what we're trying to do here. So we've got the information. Now I'm going to have to look this up because I've calculated, I've done it, I've found the code to do it, and I don't understand it, which is always dangerous. I just don't understand it completely, but I've already done it, so I'm going to just copy it. I don't think it's very complicated. Now it's called the it's really weird, but it ends up giving you the number of seconds. So we're basically doing our own ETA variable. We're adding some stuff to it that wasn't actually in the original Kerbal Operating System. Where would I have put this stupid looking thing? Probably miscellaneous functions, I think. I try to organise my libraries. Misfunctions. Oh, it's a work of art, I can tell you. Little nifty little routines that I've just picked up over time. Oh God, that one looked dodgy. All right, so it's not that. Okay, it's not that one. I might have called it orbital functions or something like that. Knowing me, and there it is, orbital functions. All right, one day I'll put all this in a GitHub. Maybe. I got problems with GitHub, in case you're wondering. So, yeah, to mean anomaly. Phew. Time to orbit position. Estimate the time for an object orbit from initial position to a final position. Well, that's useful. Ascending node vec. Yeah, okay, that's exactly what I just talked about. All right. God, I've even given a definition for it. I don't recall doing that. Right, calculate the SAM time true anomaly from vector. That sounds like that's the correct one. Calculate angle between position vecs. That sounds really good. Code found on the internet used with caution as it is not sufficiently tested. Yeah, great. That's an angle. The angle's not going to tell you much. What you want is a time. Pretty sure I have done this. Gosh. I did that in terms of the true anomaly. You know what? I'm going to have to just ignore that my library for a sec. I can't even remember how I did it. I'm going to look up the actual code that I used. That might be better. That might be prudent. I called it plane change. Right. So if I can still understand it. Time to true anomaly. Well, if I can't work it out, I'm going to have to do it as homework. You just have to take my word for it. Calculate the line of nodes. Time to orbit position. I think I know what I did. I converted it to a true anomaly, and then I work out the time from the true anomaly, which would be correct. I'm going to have to explain what a true anomaly is though as well. All right, I'll have to do that. Okay, I know what it is. Yeah, it's looking a bit, I thought it was a bit simpler than this, but obviously my memory was playing tricks on me. I'm going to have to do it in several steps, I think. Okay, so we're going to go back to this other one again. Or did I leave it open? Can't remember. No, we didn't. Right, okay. Go back to our orbital functions. Okay. True to eccentric anomaly. True to mean anomaly. Well, this is it here. Well, I'm just going to pick it up and use it. Because it's what we want. It's what we want the time to orbit position. I can see that this is going to be a useful function to handle, so I'm just going to pick the whole thing up and use it. Like so. All right, so we're going to put it in this other library. The one that I'm doing for the series. All right. Time to true anomaly. Okay. So that means I'm time to true anomaly. That means I also need the other function to convert the line of nodes to a true anomaly. There it is. Calculate true anomaly from vector. Alright, I'm just going to have to take this whole function. Well, I'm going to start off here. And see if I got enough info here to actually work it out. Right. Oh, right. Yeah. No, that's right. That's right. All right. Calculate true anomaly. Okay. Well, Got to start somewhere. Local true anomaly angle. Then we're just going to say set true anomaly angle to what I just said. And we'll just see if we can do a fill in the blanks exercise. Calc true anomaly from vec. Oops. From vec. Seeing it's complicated. Well, we've already got the orbit normal vec. It's basically our SAM2. Already got that one. They're the one and the same things. I'm just wondering why I'm passing it in again. That seems a bit klutzy. True anomaly vec would be the that would be, maybe it's just a convenience. That would be the line of nodes vec in this case. Line of nodes vec. And the eccentricity vec. Seriously? I know what it is. Well, if there was ever an easier way of doing this, I never discovered it. So true anomaly ang. So eccentricity vec. I think we need another function. Unless I had another way of doing it. Okay, where did I calculate that? I really drill down on this one. Change. I'm just a little bit worried about this code here. I never would have thought it was that complicated. Calculate eccentricity vec. There it is, right there. There it is. All right, looks like I need this one too. Just put it in there for now, in case I have to fiddle around with it. All right, I'm gonna keep closing this one so I don't get mixed up. So, cut and paste time. Let's just say we need it first. Okay, so it's going to go there. We're just going to say the stupidest thing we can do. We'll just call it ekvec. I don't want to call it eccentricity vec. Ekvec. People know what that abbreviation stands for. ECC is just an abbreviation for eccentricity. To be honest, you can get a lot of these down to one letter abbreviations, because you just use the same abbreviations that everybody else uses, and that I'll do that, but I can't remember what they are off the top of my head. But you can get a lot of these down to one character, which makes looking at the calculations a lot easier. But you've got to write a table. To be fair, you've got to write a table at the start of your program saying these are the conventions that I've adopted within my code, blah 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 blah, so you don't confuse anybody. It's the letter for eccentricity is probably not E. It's probably something else. I just can't remember what it is off the top of my head. Just like semi-major axis, semi-major axis is A, stuff like that. It's probably some Latin word. Don't worry, it makes sense. It does sort of make sense. All right, okay. And that's the least thing we could do here. What I can't understand is why I seem to have used a lot of stuff over and over. I wouldn't have normally done it that way. Okay. Right, let's just put it, yeah. Sometimes people put braces on the same line, but let's not worry about it. So we got that one. Yeah, that's why it doesn't line up anymore. Mu. Seriously. Mu's easy, that's a constant. All right. Mu is the mu. mu. It's a gravitational constant for the body. Oh, it's not quite. It's not the constant. It's they call it the, hang on, the gravitational parameter of the body. Right. Okay, but it's a constant. It's a number, scalar number. That's all you need to know. Okay, so what are we actually trying to do here? We've got the position vector. I guess if you wanted to be really pedantic, see, all these numbers will be changing over time. So you could, if you want them all sort of to be close together, you'd assign them to temporary variables just to so you don't have to do it over and over and over again. Because they'll vary just ever so slightly between, even from statement to statement. Because you got to remember the game progresses, the game moves on and does its own thing and updates these variables in here. All right, let's not worry about it right now. So we'll just, this one's clearly going to be the see, that's actually just a SAM. I obviously didn't, I must have decided to put them, spell it out. Yeah, I know what it, I know why I did what I did. That's easy. That's ship position minus ship body position. And it's a vector. All right. Well, I know that for a fact. It is a vector. Okay. Yep. And the same with this one. The most accurate. There's actually two velocities on each rocket too. That's, I've never been able to figure out exactly why there's two, but they're slightly different. I try to use the correct one. I try to use the orbital one. That's why it's gonna be yeah, that's right, that's correct. We're dealing with the ship right now, so ship orbit, we could just say OBT. I think is a OBT. Yeah, let's use the abbreviation, velocity orbit. Because there's two velocities. Right. Okay. It's just you know, if you want to be consistent. Otherwise you'll just drive people total. You know what? I'll call it orbit. I'll be consistent with orbit, even if it's a bit long-winded. ORBIT. Alright. Okay, so we'll just replace that one with the ECVEC. Oh. How are we going for time? I think I'm going to be doing a lot of homework. Yeah, if all this is just too much, just maybe wait. Maybe I'll take, it's going to take me an episode or two to get it right, but you know, if you want to know how to code, this is how you code. I mean, there's no getting around it. You got to learn it. There's no getting around it. These scripts don't appear from nowhere. So basically, I'll tell you what it's doing. What we're trying to do is work out how long it's going to take us to get to the ascending node or the descending node in the orbit. Now, the best way to characterize how the speed in the orbit is how many degrees is it going through per unit of time. So it's a rate of the angle change, because you can't use velocity because it keeps curving. And velocity goes in a straight line, so it's like it's exactly like a clock. A clock is an excellent analogy, although its trouble is prograde is anti-clockwise, just to keep everyone confused. So what we're doing is actually working out the clock for the orbit. Now there's a complication. The complication is that it's not circular. A circular orbit is a special case. It's not circular. It's elliptical. So that means that we're working out this clock, the time from the clock, but the clock speeds up and slows down depending on the where it is in the orbit, and that's a bugger. So the angle with the center of the body it can't be used. What they do is I think it was Kepler, or it was one of the other guys, worked out if he could convert this angle to another angle, which they called the true anomaly. Why they called it an anomaly, I have no idea. But that's all it is, just another angle. It's just a conversion between the angle you use if you had a perfect orbit, which is called the eccentric anomaly. I hope I got the term for that correct. They call that the eccentric anomaly, and they come up with a way of converting it into what they call the true anomaly. And the true anomaly has the property that its angular speed is constant. So to go through a degree takes the same amount of time no matter where in the orbit you are. So that way you can use it to calculate your time. So that's what they've done. That's what they've done here. Once you get your head around that concept, it all makes sense. But it's a true anomaly is the one you usually want. It's the other one, the eccentric anomaly, is considered the weird one. Yeah. All right, so obviously I found some clever code off the internet somewhere that converts between them. All right, so we need we're only halfway there. We're only halfway there. We need to work out the eccentric angle and convert that into the true anomaly. Okay, ship body position, the eccentric, the ECVEC. All right, so we need the easiest way to do that. Got the line of notes. True anomaly from vector. The angle. I think we've already got it. I got there in 2 steps. Let's do this way. Vec. kind of make it accurate for exactly the point where it's called. So we just say sets I get the feeling it's a value that changes constantly, so you don't really want to set it up here. These ones are now the SAM has an interesting property that it doesn't change. Well, why would it? It's like angular momentum, it doesn't change. Unless you change the orbit. But we're not doing that. We're not at this point in the code, so it's actually an invariant. It's supposed to be an invariant. If it does vary, then you've probably got problems. So I feel okay with calculating it once and then not worrying about it after that. But these ones might they might be a bit more fussy. We'll have to calculate them. All right, so we've now got this true anomaly. What are we going to do with it? True anomaly. True anomaly. I got the feeling I missed something here. Right, well, what we're going to do is convert it into time. Just wondering how I'm going to do that. I bet you I've already done it. I might as well just use my whole library to begin with. I converted it to a time somewhere. True anomaly from vector gives us a number of degrees. So the time is going to be, let's call it time. We called it we'll just call it node 6 for now. How long is it going to take to get to the node? Now how are we going to work it out? So it's going to be set. See, what I'm going to do is I'm going to print it out, let it run, and let's see if the value actually makes any sense. Because this is sort of the we've got to get this straight first before we can start talking about isosceles triangles and things. The timing has got to be correct because you've got to do the maneuver at the node. So yeah, this is the first thing I'm doing. So this is going to be it's a number of degrees. We've converted it to a number of degrees which we pass through. So that's going to be the orbit of the ship. It's going to be the angle divided by the orbit of the ship. I've got a fraction. It's going to be a fraction. You know what? I've already done this calculation somewhere too in this series. Hang on, I'll just use my own code. All right, if I can find it. I've already done it, so I don't have to think about it anymore. It was when I was doing the MUN contract. Seems a long time ago now. Where was it? I must have just gone straight past it. There it is. So it is here. There we go. Don't have to think about it anymore. Cut and paste programming at its as its finest. Voila. That's it. We're going to have to try this. This is a mess. This is a mess. I can already think of one problem. But let's see if we're even close. So, all right, we've defined it. Let's just put it. Okay, I'm just going to put to just test it. Sorry, how I'm going to test it. I'm just going to do this. I'm going to return the time. Return the time like this. Then I'm going to call. Just set up a little loop here and just call it. I just say print round. And I was passing in a parameter, so, and it was going to be we'll pass in the parameter anyway. Body. I think that'll do. I just want to see it actually produce something before I write any more code, you know. Two. And get down to one will do. It's seconds. Let's see if this whole ball of wax holds together. And we're going to put this in a we're just going to put it in a loop. We're just going to say wait. No, we're not going to do it that way. We'll just break out of it. And just for the hell of it. This is just solid to test it out, right? See if it produces anything remotely looking like a time. All right, let's just call it. I just want to do something other than looking at the code for 2 hours. Well, actually run something, you know, start to look at some results, you know, rightly or wrongly. How's it going to go? So run, probably crash. Oh, garbled selection. Yeah, of course it is. Oh, what the heck is that? Let's get rid of that. Oops. I don't know what that is. I don't want you to see it either. Uh-huh. I misspelled something. Position. Oh, let's start somewhere. Start debugging my bad spelling. P-O-S-I-T. P-O-S-I-T-I-O-N. Okay. Is it coming up on my screen? Yeah, it is. Okay. I can't spell from life, but it depends on it. Undefined name. Calc eccentricity vec. What? Oh, let me have a look. To calc. Isn't that what I called it? Oh, I haven't saved it. Right, okay. I have now. Go. I reckon I had problems with that program. Start from here. God. No, it's 6. All right. Oops. Right, there we go. And it's gone off into the wild blue yonder. I think I've lost it. It was thinking about it. God, why did it take so long to run? Did I leave a loop in there somewhere? Round. Body minimus. Return node 6 to plane change. Orbital. That looks alright to me. What's wrong with it? What is it complaining about? Cannot use time span where scalar is needed. Oh, I know what it is. I know what it is. It's being pedantic. Yeah. I called that time span. Okay. Yeah. All right. I could probably print out the time, it'd be just as good. I just want to see a count of the seconds, and I want to see it dropping down just like that to make it look like that ETA variable we used the other day. It's going up. All right, let's have a quick look. Well, it did something. Not quite what I expected. It should have been a second apart, so it's getting something wrong somewhere. Let's have a look. Have I actually passed the spot yet? No, I haven't passed the spot. Interesting. Which means I'm getting the yeah, I know, I spotted it straight away. It's ship it's going to be the ship ship or rotational period. Hang on, let me just have a quick look. I don't believe it's rotational period. It's going to be period, isn't it? Orbit period. Yeah, sorry. That's close. Orbit period. All right. Well, that's a curious result. Doesn't change. Which means I'm not recalculating something. Minmus. Minmus is the target. Could have put frog in there and it wouldn't have made it. Probably wouldn't have made any difference. It means ship body minus body position. I may have. No, that's correct. That's correct. Ship position minus ship body position, yeah. Orbital position. I know, I can see straight away that it's wrong. I'm trying to work out the SAM for Minmus. So it's going to be orbital position minus ship body position. Actually, no. Ship orbital body position. Just it's the same reference frame as the other one. I'm going to have to explain it now, aren't I? I'll try to explain what I'm talking about with this position stuff. A position vector in this space tells you where something is, but you need a reference point, and the reference point is the middle of the sphere of influence, which is going to be the body. In this case, it's going to be we're in the Kerbal sphere of influence right here because we're using patch conics, right? Just accept that. So the position of minmus is going to be relative to which is there's minmus there. It's going to be relative to Kerbal, right? Now, the position vector that they're always talking about in Wikipedia and that is the line between the center of minmus and the center of Kerbal, right? So it's just a line, just like that's a line. So you think about it, a line, it's like the clock, the handle of the clock, right? It just points at all times, so you know where it is. All right. Now, but the way Unity works, the game engine works, all positions are relative to the ship. So if you just say position, it gives you a line from the ship, which is you, to the object. So it's actually a line from there to there. So you can see it straight away that it's not the one you want, because it's not centered on anything. It keeps changing. But trust me, if you print out the position, it will give you a line from there to there. So it's obviously changing because this thing's going around Kerbal all the time. Now, that's okay. All you need to do is to change the basis of the vector. And to change the basis of the vectors, you just, as long as it's all done consistently, you just subtract it from the another line from the line of a line that goes from the ship to the center of Kerbal. So you just subtract it. So if you do that, you end up with the line you want, which is a line from the center of Kerbal to the line to the center of minmus. So that's why you always find this minus ship body position everywhere. It's just changing the basis for the vector. It's relocating the origin. That's what's happening. So it's just the way that I mean, most computer programs, video games, you got the player, and the player is the center of the universe. The player is the center of the universe, so it makes sense that all the position vectors are based off that player, and not some other reference frame. So everything is relative to the player. So that's the way they do it. So you just got to reposition it. So yeah, that's what I forgot to do. Now does it make any sense? Orbital position minus orbital body position. Orbital orbit velocity orbit. Okay, and then we've got for SAM2 we've got ship position minus ship body position. So I've done the same offset switcheroonie there, and ship orbit velocity orbit. Now all velocities are a little bit different. Velocities have already been adjusted. Because if you measured the velocity relative to you at all times, it'll be zero, which isn't very useful. So it's already been adjusted to be relative to the center of Kerbal. So this number that you see here all the time has already been switched. So you don't have to worry about it. So once you've just got to keep those two rules in mind whenever you do cost programming. It's all explained in the manual, by the way. It's the reference frames. You've got to get that straight in your head, though. So yeah, all right. Let's see if we get any more intelligent figures, intelligent numbers out of my test program. I can already see there's going to be a problem. It's the result's ambiguous. Maybe that's why I had all that other strange code in that routine, was to get rid of the ambiguity. Well, and that didn't change anything at all much, did it? Okay, what have I done wrong? I would have sworn that was going to fix it. Damn, alright, didn't fix it. Orbital position, my ship body position. Body position, ship, orbital, orbit, velocity, orbit, ship position. You know what I've done wrong. I'm using the wrong reference frame here. I should be saying ship orbit, velocity orbit, yep, and hang on, no, that's correct. Ship position. I'm pretty sure when they do this stuff, it's always position first, velocity second is the. I try to keep it consistent. Let's have a look what I did again in my script. Where was it? Launch to orbit. So what order did I use? Maybe I use it's the other way around. I'll find one example somewhere. Did I define what a SAM was? Probably not. Yeah, whatever it is, you want to keep it consistent. Something tells me it is actually the order is important. Pitch over. Oh, well, what am I doing? Oh, no wonder it wasn't making any bloody sense. I was looking at the wrong thing. Sorry. Plane change, wasn't it? I was looking at the wrong one. All the code just starts to look the same after a while. It's my excuse. It's position, then velocity, position, velocity, position, velocity. M match. Ship body position, ship body position. Oh, I think I know. Although, would they be different? I'm using ship body position every time. Matching orbit. I would have thought they were the same, but they may not be. They're not necessarily the same. See, I'm using the body of the orbital. In this case, I'm using the body of Minmus, but you can't really assume that. It sounds like they should be the same, but they may not be. I'm going to have to think about that. Homework. Orbital body position. You know why they might be different? Because you would have thought that Minmus's body and the ship's body would be the same origin, but this game has to do a lot of odd things to make it work. It might be treating this one differently, and it gets away with it because you're not on the body. So anyway, I'm gonna have to think about that one. That's good. Actually, anyway, I'm gonna make them consistent. So I would make that ship body position. If that's what I did in that other script, let's see if it makes any difference. It's okay. Nope. Interesting. No, it's decreasing though. Curious. All right. Okay. What have I done? True anomaly divided by period seconds. So I should be getting 240 approximately. We should be getting one figure or the other figure. One figure or the other figure. ship position, ship body position, my ship body position, orbital. Just for the hell of it. That's just for the hell of it. It's just funny because the number is kind of in the ballpark, which implies that I could be close. I think the order is important. Getting different results. Yeah, okay. It made a difference. All right. All right. So we might have made a mistake here. Oh, um, the ship position, ship one. You know what? Probably should have. Let's try it. Got the same, pretty much the same result there. Weird, huh? I don't think anybody's game to get jump in the comments and tell me what I'm doing wrong. Other than trying to attempt something like this live. That was mistake number one. That was mistake number one. All right. Ship orbit, velocity orbit. Ship position minus body position. Line of nodes, vec. True anomaly. Not an order of operations thing. Body position. Ship position minus ship body position. Ship orbit, velocity orbit. I assume that's the correct velocity. Right, hang on. Okay, let's work backwards. Let's work backwards from this. Time span, which is a period of time, that's seconds. I'm trying to convert the ship's position in its orbit into an angle, like a clock hand, or just one clock hand. And I then want to convert that back into a period of time. So one time around the clock's 100, say, and then that means that would take you the ship orbit period. Which is in seconds. In case you're wondering, 30 odd minutes. There might be something a bit strange. You know what we would do, what I would do next is I would print out all the values one at a time. We already know that value. And just check if they don't look weird. When you're doing this commercially, you've got debuggers that let you set checkpoints and things that they'll display. You can single step through your code and they display all the variables for you. You just push a button, but we don't have that. We've got to do it ourselves. So it's not very efficient, but it gets the job done. So you just say print. I'd say just see if it looks like a reasonable value. You can round it off if you want to, but I don't think it's all that important. That looks all right, actually. That doesn't look too bad. I'm not saying it's the correct value, but it looks like an angle. Is it increasing? Yeah, it's increasing, as you'd expect. See, all right, all right. What I was referring to earlier, I'd already saw an issue. The it's a bit ambiguous, isn't it? Which node are you talking about when you do your calculations? Are you talking about that node there, or are you talking about that node there? So clearly, some of that other scruffy looking code was to resolve that issue, was to work out which node you're actually referring to. Probably you had to say, well, I want to do the calculations from the descending node, or I want to do the calculations from the ascending node. So you probably had to pick one or the other, just to keep it all consistent. You know, if you want the other one, you just subtract or add 180 degrees, whatever takes your fancy. That's not too bad. So yeah. So if it's increasing, it's about 170. Which, ooh, that doesn't look good, does it? Does that fit anywhere? 90, 90, 270, not 170. Yeah, that figure might be off. That's true. Does it fit anywhere? Not really. It's roughly 180, so well, what we can just do is time warp the ship to it gets really close to one of these nodes. And then have a look at it. You can see it, I can't see it. Does it seem to be making any sense? It only went up a little bit, didn't it? Which means, right, okay. So I might say I could print out the eccentricity vector, but it's not going to look like anything to anybody. Yeah, it's like it's like we're picking up the value from Minmus, the value of Minmus, not the value of the ship. Something like that. And how would that even be possible? Ship position, ship body position, ship orbit, velocity orbit, ship body, mu. I reckon that so true anomaly ang. Orbit normal vec. Okay, I try to adjust for the quadrant and everything, which is good. You know, quite often when you do trig calculations, you end up in the wrong quadrant. That's good. That's good. I try to allow for the quadrant, which quadrant it's in. It's a pity that I just said orbit normal vec without saying which orbit. I assume it means the orbit that we're looking at. Orbit normal vec. It's saying that the eccentricity vector is pointing to the periapsis. Yeah, it probably is. You've got to start somewhere. The periapsis is quite often used as a reference point in a lot of calculations because it doesn't change. If you think about it, the apsis do not change until you change the orbit. So that all makes sense. As long as you're pointing in the right direction, of course. It's a true anomaly vec. Vec. Eccentricity vec. I've got the wrong eccentricity. This is a true anomaly. Yeah, I know what the problem is. That's why it's not changing much, because all I've done is worked out the where the line of nodes is relative to the periapsis, and that would not change. It might float around a little bit, you know. Yeah, that's wrong. That line there's wrong. For sure. But I'm working out the eccentricity vec. Okay, let's have a look at eccentricity vec. Time to orbit. Think of this as a line of the body periapsis, position vector followed by velocity vector followed by mu. Okay, so line of nodes. Hang on, I'll shut that other one off. That would be the line of nodes. Ship. Body position. Oops. Be consistent. G. Oh, I haven't defined it yet, sorry. Yeah, I'll find out the abbreviations these things are going to get. Oh, I did it again. Oh, yeah, no, that's why I'm doing that. We'll just call that one node for now. I don't know if it's the AN or the DN yet. I think some of my code's trying to work that out. I just say set anomaly ang, set ship ang, set ship anomaly ang. Supposed to be a readability aid minus node ang. Oh, actually, we will. We should. Let's just call it. Let's call that one. Oh, I can't even think at the moment. It's probably my dinner time. Yep, I thought so. Oh, okay. Can't think of a good term for it yet. See if this works. Then I'll wrap up. If it doesn't work, either way, I'll wrap it up. Just let's just say diff will do. Right, I think you can see what I'm doing, where I'm going with this. I explain. If it works, I'll explain it. If it doesn't work, I won't explain it. Because I'm probably still wrong. Yeah, I mean, all the terminology looks weird, but once you get, it's better to just get the concepts right in your head. And then it's not so hard. It's not so hard. And scribble out some diagrams on a piece of paper. That always helps you. I think my biggest problem with trig is I can't figure out how to handle the different quadrants. I'm all right as long as it's in the first quadrant. Then I just go to pieces if there's any other quadrants involved. I find vectors a lot easier to understand. What? Oh, yeah, bloody misspelling the stupid thing. Position. Where did I go and misspell it? Oh, right. Position. My ship body position. Sometimes you got to reverse these things. Come on. Seriously? Buffer can't be that large. All right. Looks better, don't you think? Yeah, all right. I reckon that's it. Yeah, I was just working out. All I did initially was I just worked out the true anomaly of lines that I've defined not to move. Like the line of nodes doesn't move. Or it moves very slowly. Sorry, I should say. So actually, no, it won't move. It won't move because it's defined on the plane. The line of nodes won't move until you change, and you're not going to change Minimus's orbit in a hurry. You can change it if you want to, but you just go into the configuration files and change it. But you just got to know where they're hidden. Yeah, so the line of nodes is an invariant for a particular orbit, which is good. It makes it a bit easier. It won't change. The only things that are going to change is the position of ship. It's going to go around the clock. So while it's heading towards one node, it's heading away from the other node. So its value could be increasing or decreasing. Obviously, you've got to resolve that node ambiguity at some point. So all I did was calculate some fixed positions. That's why the numbers didn't seem to change very much. They might change a little bit, but let's not go into the reason why that might be the case. So what I had to do was I had to calculate this line here, the true anomaly for the node and the true anomaly for the ship, and then subtract the two to get the remaining distance, and then I convert that into a time. I think it sounds simple, doesn't it? But look at all these different things you've got to take into account. That's why the code is a bit strange. But you need that information because you got to know when you're going to, if you're going to do the plane change at the node, you've got to know when to switch the engines on. It's worse than that. You've got to know how much you're going to burn and do the old thing like in my launch to orbit script, like I did with the apoapsis, you could do the similar thing, and you get inaccuracies and all that creeping in. But anyway, we'll deal with one thing at a time. So um, clearly I had found the code. I do understand it. It's just you just got to get your head around it. It's not that hard. You know, if you're not familiar with vectors, this would be impossible for you to work out till you understand what a vector is and all that. But a vector is just a line, really. It's a line with a length. Okay, it's got a magnitude, as they say, and points. It can point anywhere. But the way this game makes sense of things is that it defines origins, and pretty much the origin is defined as the center of each SOI. That's why when you go from one SOI into another SOI, things seem to change. It's because it's shifted the if you go out of the Kerbal SOI, you then end up in the SOI of Kerbal, which is the sun. So it's clearly things are going to shift. It shifts the origin from there to there. Everything's going to look a bit different. Yeah, so that's why that's happening. That's why you got to understand the vectors and the way they've been used. All right, so we're getting very close. Oh, we're just past the node, have we? All right. I don't know if the value's correct, but it seems to be, except that it's negative. You might be able to use that to your advantage. That might tell you which quadrant it's in. Oh God. Sorry, that's the time. That's the time, isn't it? Yeah. What I can do. I know what I can do. Just for shits and giggles. Let's not worry about the ambiguity right now. This might make it look a bit better. Just take the absolute value of it. One way of getting rid of a negative sign you don't like. Just take the absolute value of it. So just to make things, I'm wrapping up, but I just want to make things clear. You know, you should really do this before you do prints. You should print. You just say, let's say, print. Otherwise, you'll get so confused. Should do something like this. Let's just make it one. Now, what is it? It's a degree. It's degrees. You just need to do this. All right. Okay. It's print. Yeah, it's degrees. All right. And this one is print round. Seconds and 6. Make it look like I know what I'm talking about. How does that look? Well, they look the values look okay. If you go and print out an angle and you get something that's greater than 360 degrees, you might have problems, but just remember some formulas wrap around. You can't assume that that automatically makes it incorrect, but you might mean that you should have a closer look at it. All right, so the degrees is going down and the number of seconds is going down. Yeah, let's just let's get it about. I reckon it's calculating everything from the descending node for whatever reason. Let's just fast forward it to about a known value, let's say 90 degrees approximately, and see if that gets reflected in the figures. If it doesn't, then I've got problems, still got problems. So I'm expecting an angle of 90 degrees in this test case. Just trying to get it straight. Around 90 degrees. Yeah, there you go. And I said the period's probably correct. Yeah, all right. It looks like, yeah. So I've got some work ahead of me. What I'll do is, unless somebody asks me really nicely to go through it, my homework would be, I'll go and sort this garbage out. I honestly thought it was a bit easier than this, and when I looked at my code, I was horrified. So if I know what my own code looks like. If it looks like that, it means I had issues. So when I wrote this program initially to do the plane change, now, so I'll sort this as my own homework. I'll sort this function out. I'll resolve the ambiguity and all that. If somebody wants me to do it online, just let me know. But I reckon you're mad. I'll sort it out and write a proper function, so it'll give me back a nice time, and I know that I'm actually referring to sort out the ANDN ambiguity. AN and DN. All right, I'll do that as homework. So the next thing I'm going to do, next episode now, because you got to do a plane change. I'll just summarize it very quickly. What I'm going to try to achieve. Now you got to do a plane change to line it up with this line here. You already know you have to do the plane changes at the AN and DN. That's the easiest method. There are other methods to do out of plane changes, but I'm not going to bother. I struggle enough with just this, so we're going to have to do some sort of burn. Now, I guess the easiest way that they get you to do is just to burn upwards. Say if I want to do upwards or downwards. So either burn what they call normal or anti-normal. Which is, I don't have it on this. I haven't even unlocked it yet in career mode. So they tell you to burn pretty much normal or anti-normal to change the plane, and yeah, it will work. But it's a very poor way of doing it, because it's not the correct angle to use. What'll happen? It'll cause your orbit to change shape as well in a fairly predictable manner. I can't remember it. It advances the the I'll have to do it. I have to do both methods and find out what it does. It anyway changes it moves something, and that's probably not good. Because that's not what you want. All you really want is for the inclination to change. You don't want some other orbital parameter to change. And it might change. It'll change the shape of the orbit. It might change the apoapsis or the periapsis a bit, or it might make a nice circular orbit a little bit elliptical or something like that. I can't remember what it does exactly, but it happens. So it actually distorts your orbit. So what you do is they're clever cookies. The people worked all this stuff out. You use what's called the isosceles triangle method. You don't burn normal. You calculate an angle, which it's approximately normal, but it's not. It kind of tilts back on itself a little bit. Once you calculate it all out, it tilts back slightly. So it's actually normal, but tilted backwards a little bit. So it's an isosceles triangle, not a right angled triangle. So that'll be the method I'll be coding, and it works rather well. It's what they call a pure inclination change. I guess if you're just playing this game normally, you could attempt it, but you'd have to calculate it first. I've never seen it in the game itself, but I was aware of it because I watched somebody's lecture on orbital mechanics, and they talked about it. They don't like accidentally changing the shape of their orbits just because they want to make a plane change, because they have to make plane changes all the bloody time, because for the simple reason that most of the spaceports are located north of the equator. So it'd be great if they could have built all the spaceports on the equator, but they weren't. It just wasn't convenient for them to do it, especially Russia's the worst. Russia's worse. It's got its launching pads a long way north now, and a lot of the useful orbits do go around the equator. The trouble is you can't launch from north of the equator into the plane of the equator. The geometry just doesn't work. So they have to do inclination changes all the time. So it's not surprising that they understand them very well, because they would have figured out a way of minimizing the amount of fuel they have to burn. That's one reason why the International Space Station is in the orbit that it is. It's not in a nice equatorial orbit. It's in an orbit to make it accessible. Well, they're thinking about the Russians, I guess. So it has to be accessible within reason from their launch pads and the North American launch pads, and even the I think the French have got some launch pads that are a bit closer to the equator. I can't remember where it is now. It's in Equatorial Guinea or somewhere. I can't remember. And now you've got. Now they're launching rockets. Well, they're not launching to the space station, but they're launching rockets from New Zealand, and they're planning to launch some rockets from Australia too. But we've put our launch pads up in Queensland in the tropics. We're trying to get it close to the equator, as close as we can get. Within reason, because with a launch pad that's out in the middle of Billio, out in the middle of nowhere, you got to transport all your gear out there all the time. So it's all quite fascinating. So they have to, in the real world, they have to do plane changes all the time. But apparently, what they do is they use the computers. They figure out all the course changes they've got to do, and they combine them somehow into one big polynomial or something, some crazy thing. But clearly they don't have their rockets sort of doglegging all over the place if they can help it. It costs fuel, and every kilogram of fuel means one less kilogram of payload that you can boost up to the space station or something like that. So yeah, it's not surprising that somebody's come up with a better way of doing plane changes than doing a normal burn. Alrighty, okay. I'll catch you next stream. I'll have to see what this one looks like. If it looks like a total dog's breakfast, it probably does.